Hi, this is my electric car, which is a 1988 Soleq Evcort based on the Ford Escort. In a previous video, I repurposed the original tachometer into a running ammeter to measure the current to the motor. But I still got two dead meters. One is the fuel gauge as well as the temperature gauge. So now I'm going to try to reactivate those as well. So of course the fuel gauge will want to convert into a state of charge meter for the traction pack. And then the temperature we'll want to use to indicate the temperature of the battery, because you're not supposed to charge the battery below a temperature of about 32 degrees Fahrenheit or 0 degrees centigrade. Of course, I've got both the state of charge and the temperature available here in the software for the battery manager. But it's not terribly convenient. I've got to boot up the computer each time to read it, and it's certainly be a lot nicer to have those measurements available right on the dashboard. Okay, so I got an extra instrument panel here from a junkyard, and we'll just use that to experiment. And let's just first see what kind of voltage we need to drive these meters. And just to make sure we're not connected to anything else but the meter, I'm going to disconnect these. These are meters connected to the circuit board through a nut on the screw terminal here. So I'm going to put a little fiber washer on there, which will insulate it from the circuit board so that we can test just the meter. Okay. And then put some clip leads on there. So let's first just measure the resistance of that meter. Oh, 13 ohms. A little bit lower than I thought, but okay. So let's test the deflection here. Got an alkaline cell that'll be about 1.5 volts. So it looks like that's going to be just about 1/4 full. Let's see what 2 cells in series does. And it looks like that's going to be right on full. Let's just get a quick measure of the currents. Okay, so about 200 milliamps. Okay, so what we need is between 1 and 3 volts at 200 milliamps to drive this meter. When I converted the vehicle from lead batteries to lithium, I installed an Orion battery management system. In addition to controlling the charger and balancing the cells, it has several analog outputs, and one of them is a 0 to 5 volt signal corresponding to 0 to 100% state of charge. We can't connect that signal directly to the fuel gauge because it's limited to 10 milliamps output, so we'll need to amplify it. Instead of a custom circuit, I'm going to use this DC instrumentation amplifier. It's based on the AD620 op-amp chip, and it allows you to adjust both the gain and the offset using potentiometers. It needs a power supply of anywhere from 7 to 24 volts, so we can just use the car's 12-volt accessory power supply, which is about 14 volts. It needs an input signal of 0 to 300 millivolts, so we'll have to knock down the 0 to 5 volt signal from the BMS with a voltage divider. It has an adjustable output of up to 7 volts at 14 milliamps, which is still too weak to drive the meter, so we'll link it to an emitter-follower power transistor with the fuel gauge as load. That will clamp the voltages across the fuel gauge at 0.6 volts below the op-amp output. The gauge draws a maximum 200 milliamps, and I'm using a transistor with a current gain of 60, so the maximum current load on the op-amp is 1/60th of 200 milliamps, or 3 milliamps, which is well below its maximum rating. To maximize battery lifespan, I normally only charge up to 3.4 volts per cell, which is 82% state of charge. That gives a 4.1 volt signal from the BMS, which the voltage divider knocks down to 124 millivolts going into the op-amp. I want to set that to the full position on the fuel gauge, so we need to adjust the op-amp output to 3.6 volts, which the emitter follower will reduce to 3 volts going into the meter. 0% state of charge is defined as 2.8 volts per cell, so a 0 volt signal should correspond to empty on the gauge, which means 1.6 volts coming out of the op-amp and 1 volt on the meter. Okay, I've got the circuit wired onto a Mockup board here. It's got a 6 volt power supply, and put that through a 10K pot here. That'll give us our 0 to 5 volts as the signal, and then that's going into voltage divider here, and then that input is going to this AD620 board. And for a power supply, 14 volt power supply, we have this old Dell computer monitor power supply, 14 volts. So this is going to measure the input voltage that we can again adjust between 0 and 5 volts. And then, so after the voltage divider, 4.1 volts input, that should give us 124 millivolts here. Okay, that's about right. Well, here's our power transistor, but before we do that, let's go ahead and calibrate the op-amp here to give the output voltages that we want. Okay, so I'm going to plug in the 14 volts here. And let's just measure that supply. Okay, that's 14 volts. Okay, let's just turn this to 0. And then this should be the output of the op-amp. So 1.12, and when that's 0, we want this to be 1.6. So this is the 0 adjust. Okay, 1.6. And then when we turn this to 4.1, want this to be 3.6, so that means adjust the gain. Okay, 3.6. Let's try the 0 again. Oh, now the 0's off a little bit. Bring that back down to 1.6. Just back up to 4.1. And now that's a little low, so I'm just going to go back and forth here and try to get these both to the correct value. Okay, so 0, 1.6, and when this is 4.1, that's 3.6. Okay, so I think I got this adjusted, and now I'm going to connect up the power transistor to the meter. Okay, I've got the power transistor and the meter wired up. I'll just apply the 14 volts here. And we're back up to 1.6 volts. And just have to wait to see what the fuel gauge does. It's a very slow response here. So I'll have to wait a few minutes. Okay, it took about 2 minutes to equilibrate, and it's pretty close, just a tiny bit below where we want it. Let's see what the actual voltage on the meter is. 1.06, which is about what we expected. But again, just a tiny bit low, so I'm going to adjust the 0 up just a bit. And again, have to wait for the meter to equilibrate. Yeah, I think that's about right. So let's go back up to 4.1 volts, which should be full on the gauge. Let's see what the voltage on the meter is. 3.14. Just waiting for it to equilibrate. Yeah, looks like it's a tiny bit high. Knock it down just a bit. Okay, I think that's just about perfect. We can always readjust it later, but it's clear that this is it's clear that this transistor is going to work just fine to amplify the signal. Just see what the 0 does here. Okay, it took a few minutes to equilibrate, but we are back on empty. The voltage is stable at 1.6. So I think we're ready to wire this up on a circuit board. Okay, I've wired up the circuit on a proto board and mounted it in this feta cheese container, which I know will fit behind the dashboard. I've made one improvement, which is to put a DC buck converter between the 14-volt supply and the power transistor. That'll bring the collector voltage down to 5 volts, which means a lot less heat dissipation across the transistor. Because what was happening is the transistor was heating up, and that was reducing the base to emitter voltage and causing the gauge reading to gradually drift upward. Now the transistor stays pretty cool and the reading is much more stable. Of course, the gauge reading will change a little bit as the ambient temperature changes from, say, 0 to 30 degrees centigrade. But the maximum change is only plus or minus 40 millivolts, so about a 2% error in the gauge reading, and I think that's tolerable. And incidentally, when using this DC amplifier and using it with just a positive input, it's essential to ground the negative input. Otherwise, it won't register the positive input properly. And I've tested it. It works just as it did in the mock-up, so we're ready to go and try this on the vehicle. Okay, so here we are in the vehicle, and I've wired up this little circuit temporarily just with clip leads. Again, the way these gauges are connected to the instrument panel is through a nut on the screw terminals. So the last time I had the panel out of the car, I isolated the fuel and temperature gauges from the panel by putting a fiber washer under each nut, connecting a wire to each terminal separately. Now I can just connect those wires directly to the new circuitry. So that's connected to the output of this. And for the input, for now, I'm just going to ground it. So this should be 0 volts coming in, or an empty tank. So just have to connect the power here. And see what happens. Okay, the gauge is moving. Again, it's a very slow response. So this should be right on empty. Okay, so it's about a minute later now, and we are right on empty. So that's working. Now we just have to find the output from the BMS to give us the level of battery charge. So there's the BMS, Orion Battery Manager, and coming out of it is this wiring harness. It has various signals for relays and so forth, and supposedly the black wire, I guess that's this wire here, this should be the 0 to 5 volt signal for the state of charge. So just have to bring this up in the front seat. Okay, here we are back in the front seat, and there's the BMS software showing that we're at 75% state of charge. So we've defined 82% as being a full tank. So that's pretty close to full. And we've got the little circuit here connected, but it's still, input is still grounded. So of course this is going to register as empty on the gauge. And now here's the wire from the BMS, and remember 4.1 volts is full. So if we measure the output from the BMS here, it's reading just under 4 volts, 3.8 volts, which is about what it should be. And now I'm going to connect it to the input of my little circuit here. Take this off of ground. And connect it to the BMS. So this should be pretty close to a full tank, maybe not quite. Okay, that's about a minute later, and it's a little bit above 3/4 of a tank, between 3/4 and 7/8 of a tank, which is just about where it should be. So I think we have a state of charge gauge now. We just have to wire it up permanently. But First I'm going to charge it up to full and see if it really registers right at full. Okay, we're up to 82%, which I've defined as fully charged. Let's see what it says on the fuel gauge. Okay, I think that's stabilized, and it's just a little bit below where I'd want it to be. So I'm going to just adjust it ever so slightly. See if I can get right on full. Okay, I've tweaked the gain control a little bit. That's this lower potentiometer here on the DC amplifier. And now it's reading exactly on full. So I think we've got this all adjusted here and ready to wire it up permanently. But first I think I'll see if I can get this temperature gauge going as well. Although the BMS measures the battery temperature, there's no analog output suitable for driving an analog meter, so we'll have to measure the temperature directly. We'll use the same emitter-follower circuit with an identical DC amplifier, but now the input will be a small voltage from a voltage divider that includes a thermistor, whose resistance decreases with increasing temperature. This thermistor has a resistance of 10,000 ohms at 25 degrees centigrade and a temperature coefficient, or beta, of 3,950, from which you can calculate the resistance of any temperature using the formula log natural R1 over R2 equals beta times 1 over T1 minus 1 over T2, where T1 and T2 are any two temperatures expressed in degrees Kelvin, and R1 and R2 denote the resistance of the thermistor at those temperatures. The specifications for the lithium iron phosphate traction batteries give a lower limit of 0 degrees centigrade, an upper limit of 50 degrees for charging. But just to be safe, I try to avoid charging below 10 degrees, so I plan to make 10 degrees correspond to the lower limit of normal on the gauge, and I'll keep the upper limit at 50 degrees. The thermistor resistances, which I've verified experimentally, are 19,200 ohms at 10 degrees and 3,560 ohms at 50 degrees. We'll use the 5-volt supply we already installed for the fuel gauge as the source for the voltage divider. That will give a 118 millivolt amplifier input at 10 degrees and 188 millivolts at 50 degrees. So I just need to adjust the amplifier gain and zero offset so that those inputs result in the appropriate output voltage to give the meter readings we want, namely the upper and lower limits of the normal range on the gauge. Okay, so here's the mock-up for the temperature gauge. I've got voltage divider here with 2 resistors and then 2 potentiometers to duplicate the resistance of the thermistor at the 2 temperatures, and I can switch between those, and then the output from the voltage divider going into the DC amplifier, and then the output from the amplifier going directly to the power transistor, and the emitter of that transistor connected directly to the temperature gauge. So the amplifier powered by a 14-volt supply, the power transistor powered by a 5-volt supply. The same supply then powers the resistance bridge. And then the digital multimeter is measuring the voltage going to the temperature gauge. So now we've got the 3560 ohm potentiometer in the circuit that duplicates the resistance of the thermistor at the high temperature of 50 degrees centigrade, and we can see that now the temperature gauge is right at the top of the normal range, which is what we want, and I can switch that to the 19,000 ohm resistor, which is the resistance at the lower temperature, 10 degrees centigrade. And you can see this is slowly coming down. Okay, it's about a minute later, and now this is exactly at the lower end of the normal range, which also is what we want. And I set this gauge just by adjusting the zero offset and the gain of the DC amplifier. So I adjust the zero at the low temperature and then adjust the gain at the high temperature. Go back and forth until they converged. So again, it seems to be working, and just have to wire it up on the circuit board. Okay, we're all wired up and assembled, and just doing a final bench test. We've got just the 14 volt supply with the internal 5 volt buck converter. Got the probe connected and the temperature gauge reading in the middle there as it should be. We're about 25 degrees centigrade here. And the fuel input is still short of the ground, so it's on empty. And if I just grab the temperature probe, we can see the gauge slowly rising. If I take the fuel gauge input, put in a 1.5 volt battery, that should register at about 3/8 of a tank. And after about a minute, that's just where it's reading. So it seems to be working well and ready to put it in the vehicle. Okay, so we're all finished here. I've got everything installed. I've got it connected to the main accessory power supply through a 1 amp fuse. I've got all the wiring strung underneath the carpet. I've got the electronics stashed back behind the dashboard. I've got the temperature probe positioned straight in the middle of the rear battery pack. And if we look at the BMS software here, we're at 69% state of charge. And if 82% is a full tank, then 69% is somewhere between 3/4 and 7/8 of a tank. And we're at 25 degrees C for the batteries. So if we look at the gauges here, the fuel gauge is right between 3/4 and 7/8 of a tank, which is where it should be. And the temperature is in the normal range, a little bit closer to the bottom as it should be. I'll have to wait until the winter to calibrate the temperature gauge at 10 degrees centigrade. I can use the reading from the BMS software as the standard. I've also used some self-stick laser printer labels to change the label on the fuel gauge to read a battery, and I've also altered the gas pump icon to look more like a battery. So anyway, that's the completed system. It's a lot more convenient than booting up the computer each time. Of course, every car is going to be a little bit different, but I think these fuel gauges and temperature gauges, at least through the 1980s, are all pretty similar. They run on about 5 volts. They have fairly low resistance. So I think this system should work for really any 60s, 70s, 80s vehicle that you care to convert to electric. Thanks for watching.